Okay, so now we're going to talk about some application of derivatives. Well, we saw some application from the previous sections of related rates and differentials, but we're going to kind of go more into some other applications. And one of the biggest things about an application of the derivative is about maximum and minimum values. So, I mean, as you can expect, maximizing something and minimize something will be pretty important, right? If you have you want to maximize profits or minimize expenses, right? If you have a function of profit or expense, you might be able to use calculus to to maximize or minimize these things. So so we have a hopefully a basic notion of what a maximum or minimum value is. So just first of all, just in this picture here, where's the absolute? So we call this the absolute max. Where's the maximum? -1 is a max, yeah, but not 0, but whatever this value is here, right? So it's at x equals -1. So I didn't give a y value, so I'll just call f of -1. How about, yeah, so that's up here, right? So this is the biggest y value. How about the absolute min? So which y value is smallest? Yeah, 4. It's at x equals 4. And so the minimum value is f of 4. And that's down here. This is the smallest y value. So to give like a proper math definition of absolute max and absolute min, this is what we'll say. So for right now, this just looks like a unnecessary definition because it's so obvious what max means. But we'll say that f of c is maximal, is an absolute max, if for all x in the domain of f of x is always going to be less than or equal to f of c. This is how we're defining absolute max. So is that true for this one? Look at all other x values. If f of -2, f of -5, f of 3, all those f of x's are always less than f of c. So that's what makes f of c maximal. So similarly, the math definition for absolute min is f of, let's call it b maybe, is an absolute min if for all x in the domain f of x is greater than or equal to f of b. Okay, so similar deal. Look at all x values in the domain and look at f of them. All these x values, or all these y values, are always greater than this y value at 4. So that's what we're defining as an absolute min. Okay, so just questions on those math definitions. It's important to have those definitions because we'll kind of talk about a scenario when a function does not have a maximum or minimum. So it might be hard to talk about it without this definition. So let's give a scenario where there is no maximum or minimum. Which may feel kind of weird, right? If there are values, of course, something should be maximal and something should be minimal, but that's not always the case. and it's because of this definition. Okay, so this is a weird one. Can someone say why you think there's no absolute max or min? Yeah, so what about the hole tells you that? So there is a hole. So if the hole was filled in, then it would be an absolute max. So yeah, so like, why not based on like this definition? Why would there not be an absolute min? What about the hole makes it makes an absolute min not exist? Again, I kind of look at the math definition. It's not greater and lesser, but right here, there is no value greater than here. Where the f of x where the hole is higher. Well, there's no f of x here, right? Like if this was, let's say this is A and this is B. F of A does not exist. Okay, here, let's call it C. F of C does exist. It's up there. But that's kind of the key point. If there was an absolute min, can you look at it? Like, surely there's still something down here, right? And surely there's still something up there. But you can't point at it, right? No number satisfies the condition. F of x less than f of c, or f of x greater than f of b. Or I shouldn't use these letters, but yeah, so it's kind of like saying like, I mean, it's kind of our talk of calculus, right? You cannot describe a point away from another point, right? If there was an absolute minimum, right, it would be the point next to that point, but that doesn't exist. So absolute mins and absolute maxes do not need to exist, and usually see that with like holes or sometimes like asymptotes or something. Yeah, so just be aware of that, even though there might be a value that might look like there should be an absolute minimum or absolute maximum. If you cannot point at, if you cannot actually describe the point, where it's maximal, or minimal, then it does not exist. Okay, so let's do an example. Just another example. Okay. Where's the absolute max, if it exists? Yeah, I didn't give any numbers to this. Okay. Absolute max. Mm, I think so. I think there's an absolute max. I don't think there's an absolute min. Yeah, that's fine. That is fine. At x equals 2 and x equals 4. Right, the max is referring to the y value, right? So the max is f of 2 equals f of 4. The maximum doesn't need to be unique, right? If they're the same thing, or the x value of the maximum does not need to be unique. The maximum is referring to the y value. So these are maximum. Yeah. Okay, so how about the absolute min? None, correct. Because this is can't point to a value. However, what's interesting about this problem is that this is an interesting point here. Right, in some regards, that kind of looks like a minimum. Right, if I zoomed in, what happens if I zoom in at that point? So now we're zooming in. So zoomed in and ignoring the rest. Right, this is what we're going to call local. Ignoring the rest of the function. This value here is minimal. Oops. Minimal. So locally. So locally is, the word locally just means how it sounds, right? Local to that little region, it's minimal. But it's not globally minimal. So global just means for the whole function. But locally it is. So yeah, does that make sense? So local, so we'll call this local minimum. So f of c is a local minimum. If there exists a small enough interval containing C and for all smaller intervals. So there's at one point you can go small where, like this picture. So if you go small enough and you get this kind of minimal behavior, it's also going to be true for even smaller. That f of c is less than or equal to f of x for all x in this interval. We'll call it like AB. Okay, so, and then of course local max has the same, has a similar definition. Okay, any questions on that? So it just means if you, I like to draw a little circle. If you draw a little circle around the point, if that point is the smallest, then that's what's local minimum versus local maximum. Okay, let's just draw it again. Okay, so if this is a local minimum, can you see any local maximums? Maxima? So what were the points again? 1, 2, 3, 4, 6. Can you see any local maximums? State the x value where a local max occurs. Yes, also 2. Even though this was considered to be an absolute maximum, right, it still obeys the definition of a local maximum, right? If you draw a little circle around it, sometimes math people call that neighborhoods, because it's a little neighborhood of the function. It's maximal there. Anywhere else? Good, yeah, also 4. So this one's funny, right? Because it's not continuous, but that doesn't matter. These things don't have to be continuous to be maximums. It still obeys the definition, right? Right, because so the small enough little region, the rest of the function is down here, right? So this is why I like the little circle trick, is because you can zoom in right at the point. Right, the rest of it's down here, which does not even exist in the circle, so who cares about that part of the function? Right, technically this is the region I'm looking at. Right, when I'm drawing the circle, but it's like, who cares about this stuff? Okay, anywhere else? Is there a local max or local min? So I may have drawn it differently. Here. What value is this, you think? What type of value is that? That's a minimum value, right? Look at all points around it. Do you agree that it's still the smallest in that little interval? even though there's nothing exists to the right of it, right? It still satisfies that definition. This is why I like the little circle trick. It's because you can just draw little circles, and then that determines, and you can see easily how things are maximal or minimal. Okay, so questions about that? Does that make sense to everybody? Okay, great. Okay, so let's do so this is a theorem. We're not going to prove it because it doesn't really need to be proved unless you're really particular. I think it's kind of obvious. Extreme value theorem. Okay, so if you have a function that is continuous, on a closed interval, we'll call it AB. When I say closed interval, it's the brackets. Then there must exist an absolute max and an absolute min. Okay, so this one didn't have an absolute max or an absolute min, right? Why? Or why does this not obey the extreme value theorem? A couple of reasons why it doesn't. Good, yeah, one, it's not a closed interval. So automatically it's not a candidate for the extreme value theorem. And what else makes it not a candidate? It's not continuous, right? However, this one had an absolute max and absolute min, right? But I don't know, I couldn't make this an open circle. Why was this okay? It's because the extreme value theorem doesn't go both ways, right? If there exists an absolute max and absolute min, that doesn't necessarily mean that the function is continuous on a closed interval, right? It's not. There's no converse to this statement. Okay, so let's just do an example. So no matter how much you draw your shape, there's always going to be some, actually I want to do something different, maximum or minimum value. So where's the max and where's the min? Absolute. Yep, 8 for max. So there's the max. And where's the min? Yeah, 14. Good. Okay, so let's do just a couple examples where we do not have maxes or mins. Okay, does this have an absolute max or min? Nope. But it's continuous. So how does this not obey the extreme value theorem? Yeah. Not on a closed interval. Let's do another one. Okay, does this have an absolute max or min? No, it doesn't. So of course these are absolute, right? It might have something else. And why does it fail the extreme value theorem? It's not continuous. Yeah. And not continuous. Okay, so just one thing to note. Max and min, if they exist, are finite. Right? When you say f of c is greater than or equal to f of x, this thing needs to exist in the first place. Right? So if it's infinite, right, that's not a real number, so it would not exist. Okay, questions? Okay. Oh yeah, and then we can do one more. Okay, absolute max and min. Yes. Right, just because these are weird looking points, it's fine. And you know one should exist, why? Like if you ever get confused about maxes and mins, it is continuous and closed. It passes extreme value theorem. So sometimes I say extreme value theorem as EVT. Continuous and closed. Right, notice that this thing is not differentiable, but it is continuous. So you do not need differentiability for extreme value theorem. Okay. So first of all, just as an intuitive reason, why is extreme value theorem true? Well, how I like to think about it is that if something is continuous, I like to think of it as it can be made into a path, like a walking path. So why must the extreme value theorem be true? Is that if you're walking on a path from start A to end B, right? There must be at some point you go at the highest point, and some point you go at the lowest point, right? So just by the nature of continuity, nothing weird happens where you suddenly, never have a maximum or minimum value because you are walking on it, right? So I think this theorem doesn't need to be proved. To more complex math, it might need to be proved for different situations, but I think it's pretty intuitive in this realm. Okay, so let's talk about derivatives now. So the question is, when do maxes and mins exist? Its max is. So if something is differentiable, we can easily tell when a max or min exists, and this is by a theorem, Fermat's theorem. So Fermat has many theorems, but this is one of them. So this is the theorem. Suppose f of x is continuous on, not continuous. It is continuous, but the important is differentiable. Differentiable on an open interval AB. And suppose it has a max. So this is going to be local at x equals c. So the theorem says then f prime of c is, what do you think it would be? Think about functions and the derivatives, and think about all the functions that you can think about a local max, a local min. Yeah. Then the derivative is 0. So intuitively this makes sense, right? If you ever locally see a maximum, it kind of looks like that. And the maximum, it's where it turns. You think the tangent line should be 0. And similarly, locally, a minimum where something turns, the derivative settles down to 0. So this theorem proves it explicitly, without needing the intuition. And so here's the proof. Okay, so if it is maximal, if f of c, so the same is true for minimum, but I'm just doing maximal. If f of c is locally maximal, what does that mean? Then for all h, not for all h, but for some small h, h's, f of c is always going to be bigger than f of c plus h. Right? Does that part make sense? So remember, locally, if this thing is maximal, then if you go off to the right a little bit, it's always going to be smaller. That was the definition of maximal. Is that part okay? Okay, good. So case 1, let h be positive. Right? If h is negative, it could be over here. F of c plus h when h is negative. And it could be over here where h is positive. So first we're going to let h be positive. Okay, so what do you think you should do? So the derivative plays a role here, right? That's the idea, that the claim is the derivative of c is 0. So what do you think your first step would be? How do you get the derivative here? Should this looks something like the derivative, right? Well, what could you do to make this look like the derivative? So remember that definition of the derivative we started with, like a month ago? There were two definitions we had. Which one do you think would work? And remember the definition of the derivative? So instead of like the geometric one, yeah, there's a change. So like what, if you think of change, you can kind of figure out the definition. It's a change of what with respect to what, right? So how about in terms of like f? Like if you write it down explicitly, okay, f of x with respect to x. But there's an actual formula, right? The formula for the derivative. What was that formula? So you can find the derivative of any function if you have this formula, right? As long as this formula works. Yeah, so the limit x approaches a was one of them, but looking at this is probably the other one. Yes, that one is f of x plus h minus f of x. So this is very close to that, right? What if I subtract f of c on both sides? Now this looks eerily like the derivative. But what's missing? What's something else I can do to make this look like the derivative? What would you do? So it's almost the derivative. So what's missing is that divided by h term, right? Can we divide by h? That's fine, right? 0 divided by h is 0. Do I have to worry about the inequality when I divide by h? Do I flip the inequality? Yes, no? You do not, right? And why do you not? Yeah, there's no negatives because h was assumed to be positive. Right. So this is true for all h, right? This was true for all small enough h. So certainly it's true for the limit. So that's the derivative. So whatever the derivative is, it's greater than or equal to 0. But we want it to equal 0, right? So what do you think our next step would be? So we want this to equal 0, but now we just have greater than or equal to 0. So what would your step 2 be? So in the picture, what haven't we discussed yet? We haven't looked at the negative h's, right? So now, when you have 0 greater than or equal to f of c plus h minus f of c, what happens when you divide by h? What happens when you divide by h? Now the inequality flips because h is suddenly negative. Right, so I'm looking at these negative h's now. Okay, same thing, it's true for all h, so it's true for the limit. So 0 is less than or equal to f prime of c. Okay, what does that mean by f prime of c? So 0 is less than or equal to f prime of z, but f prime of z is less than or equal to 0. So what is f prime of z? What's a number between 0 and 0? Zero. Right, this should look like the squeeze theorem. So that's kind of what's going on here. Okay, so when do maxes and mins exist? If a differentiable function has a max or min, the derivative is 0 there. Is that true in the opposite direction? If the derivative is 0, is it a max or min? So just answer this question, then we can take a break. Or let's take a break for 5 minutes. So meet back at 6:40. And while I take a break, think about this. All right, why don't we come back at 6:40? So anyone have an answer to this? If f prime of c is 0, does that mean that f of c is a max or a min? No, correct. Can you think of an example where this is not true? There's a couple. There's a lot. Horizontal line. That's a funny one. I would say no to that one. That like y equals 2. I would say the max and min are always 2. Okay, yeah, I like that one. I mean, you can find an explicit example, right? But what you're saying is that if you have a decreasing function, and at some point f prime of c is 0. So what you're saying is, like, if you have a decreasing function, then at some point f prime of c is 0, and then it keeps on decreasing. That would be have no minimum value. Not a min, though f prime of f prime of c is equal to 0. Okay, so actually I'm glad you talked about the horizontal line because that still obeys the max and min expression, right? F of c is equal to 2. So f of c is greater than or equal to f of x. And f of c is less than or equal to f of x. It's okay, max equals min. So, right, it's the or equal to was the in our definition, not strictly greater, right? But I do like that you said that, right? Because if it was or equal to, then I would agree then. It would not obey the max-min property. But do you have an explicit example of this? So you have a decreasing function, and you have f prime of c is 0. But do you have an explicit example? Like y equals, there's like two, quote, obvious ones. That we've kind of talked about. Yeah. Okay, so for this one, yeah, it could be negative x to the third. Or just to not have negatives, x to the third. So x to the third would be the increasing case of what you just said. So this is like x to the third. So you know that it's derivative. If you take the derivative, you know that y prime is equal to 0 when x equals 0. But you know that there is no maximum or minimum at 0. Is there a trig function that has this property? That you can have a 0 derivative where the function is not maximal or minimal? Tangent, yeah. Yeah, y prime is secant squared. Well, this one actually, sorry. No, the derivative is not even 0 here. Never mind. Let's see. Yeah, okay, so no tangent. But yeah, x cubed is probably the easiest one to think about, right? It's a function that is always increasing. And we'll talk about when a function is always increasing, how you can tell. But yeah, the derivative is 0 at 0, though it's not a maximum or a minimum. Okay, good. Okay, so now let's talk about how to find absolute maximum and minimum values. Okay, so when do maxes and mins exist? So they may exist when the derivative is 0. That was the Fermat's theorem. In relation to the derivative, is there another place where a maximum or minimum may exist? So think about the other problems that we've done, or the other pictures. I mean, this one is a clear one. When does a maximum or minimum exist? Is the derivative 0 here at this maximum point? Or even at this one? You know, what's going on with the derivative here? Right, it doesn't exist. So this exhausts everything, right? When the derivative does not exist, or sorry, when the derivative is 0 and when the derivative does not exist. Right, every other scenario is when the derivative is not 0 and exists. Right, so those are automatically excluded. So these are nice numbers, right? So these are when max and mins exist. So this is our definition. Critical number. So critical number of f is all numbers in its domain such that f prime of c equals 0 or f prime of c does not exist. So if you don't like the word critical number, I like to think of these as candidates for maxes and mins. So calling a critical number is just giving it a special name, but all it is candidates for max and min values of a function. All right, does that make sense? So if you think of it that way, then I think you can understand what a critical number is. Okay, it's just the candidates for a max and min to happen. So let's do an example. So find critical numbers. Of this function, x squared plus 1 over x squared minus 1. Okay, so again, a critical number is when the derivative is 0 or does not exist. So I think we need the derivative. Okay, what rule can we use to solve this derivative? Quotient rule. Yeah, so again, quotient rule is the derivative of the numerator times the denominator minus the derivative of the denominator times the numerator divided by the denominator squared. Okay, so that is 2x, x minus 1, minus 2x, x squared plus 1, squared, sorry, divided by x squared minus 1 squared. Okay, notice that there's a 2x that we can just factor out. We have x squared minus 1 minus x squared plus 1. So this simplifies to negative 2, because the x squareds cancel over the negative. And then this is minus 1 minus 1, so it's minus 2. So this is negative 2x, 4x rather. X squared minus 1 squared. So what are the critical numbers? Where is the derivative 0 or does not exist? Where's the derivative 0? Okay, solve for x. I'm not sure if you're not answering because you're confused or just don't want to answer. Yeah, I'm going to assume it's the latter. So x equals 0. And then at -1 and 1, it does not exist. Okay. Anyone confused about what I just did there? Can I get a yes or a no, just so I can feel okay about moving on, or it's okay, just okay. Yeah, as we do more questions, I'll get better. Okay. So let's this is going to be a method to find absolute maxes and mins. Of continuous functions on a closed interval. First of all, why do maxes and mins exist of continuous functions on a closed interval? Why must that be true? Extreme value theorem. So if you ever have a continuous function on a closed interval, there must be an absolute max or min. Okay, so what are candidates for for a continuous function to have a max or a min? So for continuous functions, we look at critical numbers. So this is where a function must have, a function has max or min here. What other place do you think might be a candidate for a maximum or minimum, other than critical numbers? So remember, this is on a closed interval. Let me just draw an example. What's the max and what's the min? Yeah, these are the maxes. And yeah, that's the min. So the min is a critical number, right? The derivative is 0. But these may not be critical. right? If this is a function restricted on this domain, this could be like a parabola that kind of extends outwards. And when we solve for the critical numbers, 1 and 3 would not pop up as a critical number. So when you're restricted on a closed interval, you also have to look at endpoints. Does that make sense? So just because so critical numbers may not always give you the absolute max and absolute mins, because something might be happening at the endpoints. Does that make sense? So, like, for example, like that, right? None of the critical numbers are maxes or mins, and only the endpoints are maxes and mins. And again, this could be like some kind of cubic where these would not appear as max or critical numbers. Okay, so how I like to advise you on approaching these problems is first do endpoints. Step 1. Calculate the y value at the endpoints. Because what I see a lot is that when solving for the max and min values, people just go right for the derivative and then forget that the endpoints exist, right? So I say step 1, just do the endpoints, get them out of the way. Okay, so let's do f of 3. So f of 3 is 3 cubed over 3 plus 3 squared plus 3 plus 1. So it's 27 over 3, which is 9, plus 9 plus 3 plus 1. So it's at 18, 22. And let's do f of negative 3. Okay. What's negative 3 cubed? Yep, negative 27. What's negative 3 squared? 9. Yep, just gotta make sure, remember those cube tricks. Okay, so this is negative 9 plus 9 minus 3 plus 1. So that's negative 2. So now we save these. And these are candidates for the max and min values. Okay, so now step 2. Okay, I'm going to, next page. Step 2, find critical numbers. And plug them in. Okay, so what was f of x again? It was x cubed over 3 plus x squared plus x plus 1. So someone tell me what the derivative is? Uh, 2x plus 1 is this bit. Yeah, 2x plus 1. And then what about this one? X squared, yeah. So x squared plus 2x plus 1. Okay, how do I find critical numbers? Yeah, where it's equal to 0 and where it doesn't exist. So for this one, it's who cares because the derivative exists everywhere. So the only thing is 0. How do you solve this for x? Factor. What is it? What are the factors? Oh, that's, yeah, the factor as x plus 1, but yeah, the critical number is x minus 1, or is negative 1. Okay, so we have found the critical number. There's only one of them in this case. So now plug in critical. Where do you plug in the critical number? The original function f of x, right? Because this is, we're looking for the max and min values of the function f, right? So it would not make sense to plug into the derivative because, well, we know it's 0 there. Yeah, so what's f of negative 1? So negative 1 cubed over 3 plus negative 1 squared plus negative 1 plus 1. So this is negative 1/3 plus 1. So this is 2/3. Okay, so step, what step are we on now? 3. Step 3. Compare all values. So this is our set of values. We had 22, negative 2 from the endpoints. And then we have 2/3 from the critical number. Okay. What's the absolute max? And what's the absolute min? Yep, max is 22. That's the biggest thing in this list. And the min is negative 2. All right, good. Does that method make sense? So what we're doing is we are looking at, so we have a continuous function, a closed interval. So we know that the critical numbers tell us where a continuous function might be maximal or minimal, right, at critical numbers. So now if we, in addition, extend this to a closed domain, closed interval, then we also have to consider about how, where the endpoints of the interval might give us a max or min, right, because they would not appear as critical numbers. So essentially for closed intervals, the endpoints are more candidates for maxes and mins. Okay, let's do another one. So same deal, find abs max and min, and here's the function. And here's the interval. Okay, why does this function have an absolute max and absolute min? Yes, 2 cosine plus sine is a continuous function, and it's defined on a closed interval, so that's extreme value theorem. So EVT ensures one exists. What's our step one? Yeah, check endpoints. I like doing this one first again because you might forget about it later. Okay, what's f of 0? It's 2 cosine of 0 plus sine of 0, and that is 2. What's f of pi over 2? Can someone tell me what 2 cosine of pi over 2 plus sine that is? What's cosine of pi over 2? Yeah, 0. And then what's sine of pi? 0. Okay, what's step 2? Derivative, yes. So critical numbers. So that requires the derivative. Derivative. Okay, what is the derivative? Good, negative 2 sine. And good, plus 2 cosine of 2t. This is the chain rule for the sine of 2t. Okay, we have to set this equal. First of all, does this not exist anywhere? Does the derivative not exist somewhere? Do we have to care about it, D&E? No. Yeah, derivative exists. Now, so then we set it set to 0. All right, let's see if you remember your pre-calc. How do you solve for 0? All right, so how do you solve for t? What's one step you can at least do to help solve? How can you make this look nicer? Yeah, we can just divide out the 2. And meanwhile, let's just kind of rearrange things. So I like to not put my negatives first. All right, how do you solve this? Any ideas? What do you do with that 2t? What do you think? Yeah, double angle. Okay, so this is a double angle. I know there are many double angle formulas for cosine, but I just tend to remember one of them because you can get the rest, from this formula. So that's the only one I remember, but you can derive the rest by doing one step after. So what is the one step after do you think you can do to, what do you think you would want to do? Look at all your terms here. What do you think you would want? You probably want to have everything as like the same thing, right? You have these cosines and these sines. Don't want to deal with all that. Yeah, trig identity. Which trig identity do you want to use? Yeah, so what thing are you changing? So the Pythagorean identity is good, but which are you changing? Yeah, you want to change the cosine. So what is the Pythagorean identity for cosine squared? Good, yeah, 1 minus sine squared. So this is how you get the other cosine double angle formula. The other cosine double angle formula is 1 minus 2 sine squared. But honestly, I never remember that because I think cosine squared minus sine squared is just easier to remember, and then you can just do this one step to figure it out. Okay, so now this looks nicer, right? Everything is in terms of sine and sine squared. So how do you solve this now? Why is this solvable now? So that's a hint. It's in a form where it's solvable. But before that, you might want to change this up to make it easier. Yeah, rearrange. So rearranging factors. So yeah, so normally you like your higher powers first. And then I don't like negatives out in front, so we'll divide out by a negative. Now, how do you factor such a thing? So I'm not sure what you guys like. I'm not sure if maybe if you like doing it this way, or if you like to substitute first. So whichever way is fine. Either way, what is the factorization, either in terms of u or in terms of sine? So which gets the plus 1 and which gets the minus 1? So if you don't like the sine, go to the u. Second one gets the plus, yes. Yeah, because when you expand that out, you get a 2u and a minus u. Okay, so we have, what does that mean? We have 2 sine of t minus 1 equals 0, or sine of t plus 1 equals 0. So we have sine of t is equal to 1/2, or sine of t is equal to negative 1. So what values of t make this work? Let's remember we're on the closed interval on 0 pi over 2. So who cares about all the rest of the times? When is sine equal to 1/2 on 0 pi over 2? So remember, 1/2 is the smaller of the three numbers, common numbers. So what angle gives you the smallest sine, smallest y value? That's not 0, of course. Yes, pi over 6. Yeah, the first nice angle gives you pi over 6. Okay, are there any other angles that give you pi over 6 in 0 to pi over 2? No, right? If this was on a different interval, like maybe 0 to 0 to pi, then you might have to consider another angle. But since it's just 0 to 2 pi, or sorry, not 2 pi, 0 to pi over 2, then there's only one angle that satisfies. Okay, how about this one? Sine of t is equal to -1. Is there an angle between 0 to pi over 2 such that sine is -1? No. So the only critical number we have is pi over 6. Okay, so what's our last step? Yeah, so plug critical number into original. So what's f of pi over 6? Forget what our original was. 2 cosine plus sine 2t. 2 cosine pi over 6 plus sine of 2 times pi over 6. Okay, what's cosine of pi over 6? Yep, root 3 over 2. And then what's sine of 2 times pi over 6? Sine of pi over 3? It's the same thing, right? Yes, root 3 over 2. All right, so the answer is 3 root 3 over 2. All right. Got any questions about that? All right, so what's our last step? Yeah, compare all numbers. Okay, so we had, was it 2 and 0? And 3 root 3 over 2. Okay. How do you know which is bigger, 2 or root 3 over 2? Without a calculator? If we were in person, I would do no calculators. So one thing you can do is square them. So one little trick, if A and B are greater than 1, then A greater than B implies A squared is greater than B squared. It's not true for, not true for, actually that's also true, obviously, for smaller numbers, right? It's if A and B are positive. It's even true for fractions, right? Because x squared is an increasing function. So this is 4 versus 9 times 3 over 2. 4 versus, what's that, 9 times 3 is 27. So it looks like this is bigger. Okay, questions about that? Oh, over 4, my bad. Over 4. All right, is it still bigger? Yes. Wait, is it? Yeah. Yeah, 16 over 4. This is 16 over 4. Yeah. All right, everyone see that? Just a way to do it without a calculator. Yeah. So what's the max? Don't do the square one, but yeah, 3 root 3 over 2. And what's the min? 0. Okay. So that's all the time today. So next time we'll continue. It depends. I mean, don't get too scared of trig. It'd be important to understand. It's not complicated if you know your trig laws, right? And this is something like from at this point down, right? This is something maybe from like pre-calc. So I don't want to say like, oh, it's just too hard for a quiz, but at the same time, it might be too long for a quiz. But I don't want you to not study it because it may not be on the quiz. Like on an in-person test, this would definitely be on. I think I even asked a question like this on an in-person class a couple semesters ago. But the quiz has seemed a bit different than kind of how I would do my tests, just mainly because it's shorter. So they kind of it's kind of restricted on kind of the types of questions they can ask. So based on time, maybe not, but based on material, I would it'd be good to know. I was kind of annoyed there wasn't any trig on the first quiz, but that may not be true for all the quizzes, so anyway, oh, I'll stop recording.